The exam that we decided to have on Monday might be switched to Wednesday. How many people prefer that? Okay. Could be much better to have it on Wednesday because I have time limitation on Monday. And also, that would give you a chance to ask me questions if you need to just before the exam. Yeah. So anyway, when I work out the precise schedule, I'll let you know by mail. Okay. Okay. Let's talk about degeneracy today. Degeneracy is not really an issue in computations except that it may cause cycling. But first, we need to see how degeneracy might occur in simplex iterations. First of all, let me just refresh your memory on what degenerate extreme points are. What's a degenerate extreme point? What's an extreme point? If you have a bunch of inequalities and equalities, an extreme point is defined by a set of n linearly independent equalities. If the original set already has equalities, all of them must be included in your n linearly independent. The remaining ones come from linear inequalities, but they are taken as active constraints. Okay? So if you have n linearly independent constraints holding as equalities, then that gives you a unique solution, and that's an extreme point. Now, the extreme point under consideration will be a degenerate one if actually more than one set of n linearly independent qualify to define the same point. Okay? In which case, of course, you have more than n active constraints at that point. For the case of standard form linear programming problems, where you are, say, minimizing Cx subject to constraints of the form Ax less than or equal to, Ax equals b, x greater than or equal to 0, where A has, say, m rows and columns. In this case, recall that Ax equals b supplies m of the active constraints, and x greater than or equal to 0, you need n minus m active constraints from here. So whichever ones are taken as active or as binding, those are the non-basic variables. These are the non-basic variables. Okay? And in case of degeneracy, it turns out that, well, you include certainly all of the Ax equals b constraints, but the non-negativity part gives you more than n minus m. Okay, non-basic variables or equalities. So degeneracy in standard form means more than n minus m non-negativity constraints hold as equalities. Now, if this is the case, when you have more than n minus m, of course, n minus m of them will be the non-basic variables. The remaining ones, the ones that you exclude, will be basic variables, but nevertheless, they will be at value 0. Okay? So n minus m will be non-basic. The remaining ones will be 0, but they will be basic. This will occur in the simplex method when you have a tie for the minimum ratio. Okay? So what happens in the case of a tie for the minimum ratio, just imagine you've got the simplex Tableau in front of you, and you identified an entering variable, and then you're looking for the ratios of the current right-hand side values to the entering column values for the positive entries. When you have a tie, that means 2 of the current basic variables go down to 0 at the same time when you start increasing the entering variable. Okay? So when they both go to 0 at the same time, one of them will be non-basic. You just declare it to be non-basic. The other ones, they will show up as basic variables in the new solution, but at 0 level. So let me give you an example of that, and then we'll see what possible consequences that might have. So here's the example. You can actually draw the graphical solution for this, and you can see that actually 3 binding constraints intersect at a single point, and that extreme point will be your degenerate extreme point. But I'm not going to do that. You can do that at home. So the initial, when you add the slack variables to this, the initial simplex Tableau will have the following information. X3 and X4 are the slack variables added to the first and second constraints. We begin with basic variables X3 and X4. The top row 0 equation has -3, -9, 0, 0, and 0. All right, what do we enter? This is a maximization, so if you choose the most negative one, you enter that particular one. And then you look at the ratios, 8 to 4 and 4 to 2. You've got the same ratio, 2. Okay? In which case, I happen to choose this one. Of course, you could choose the other one as well. So you just go through one more iteration. By replacing x3 by x2. And the new solution you have is 1, 0, 0, minus 3/4, 1/4, 1/2, 0, 1, 0, 9/4, 1/4, minus 1/2, 0, 0, 1, 18, 2, 0. See, that 0 tells you that you have a basic feasible solution which is degenerate. X4 is 0. Okay. Now, in this Tableau, we do not have an optimal basis yet. This is actually the optimum solution, but you don't recognize it. Okay? So you enter this guy because it's negative, And then you look at the ratios. Well, obviously, this 0 divided by 1/2 gives you the minimum ratio. So you pivot on that element. When we pivot, we get the new Tableau. Let me write it here. The new Tableau will be x2 stays. x4 is replaced by x1 now. That's the new Tableau. And there's no reduced cost at the top row. That is negative. So this is the optimum solution. Optimum basic feasible solution. Okay. Now, actually, the solution in going from the second Tableau to the third one did not really change. It's just the description that has changed. Okay. What is the solution in the first Tableau? If you just write it as a vector, you've got x1, x2, x3, x4. x1 is, well, x1 and x2 are both 0 because they are non-basic. And x3, x4 are 8 and 4. That's the extreme point under consideration with an objective value, z value of 0. In the second Tableau, the solution becomes x1 is 0 because it's non-basic, x2 is 2, x3 is 0 because, again, it's non-basic, x4 is also 0, but it is basic. So non-basic, non-basic, the other ones are basic. And the corresponding objective value is 18. The solution here for the last one, x equals, again, you've got x1 equal to 0, x2 equals 2, x3 is 0, x4 equals 0. In this case, the non-basic ones are the last two components. The first two components are, of course, basic, okay? And the objective value for this one is also 18. And obviously, this solution and that solution, they are the same, okay? So this solution is precisely the same solution as that one. As I said, you did not get out of this extreme point. You are staying in the same extreme point. But this particular Tableau is described by a basis consisting of the columns associated with x2 and x4, whatever they are. What are the columns associated with x2 and x4? x2 column is 4, 2. x4 column is 0, 1. That's the basis that defines this Tableau. Whereas the last Tableau is defined by a basis matrix of x2 and x1. So 4, 2 is still in. x1 column is 1, 1. It's different, okay? And this basis did not allow you to make a conclusion about optimality, whereas this basis did allow you to make a conclusion about the optimality of that point. So the same point, nevertheless, you need the right basis information to be able to conclude that it is an optimal solution. Okay? So that illustrates that. And one important message here is that degeneracy may cause cycling. How does that happen? Well, without degeneracy, for a minimization problem, what happens is if you begin with an objective value of, say, z0, suppose z0 is the initial objective value corresponding to the initial basic feasible solution that you begin with. Since you're minimizing, and when you don't have any degeneracy, you always move to a new basic feasible solution, which is definitely better in objective value than the previous one. So if z1 is the objective value in the first in the Tableau right after the initial solution, it's smaller. And the next one will be smaller, so on and so forth. This just keeps going until, say, in some iteration k, you end up with the optimum. Okay? You stop. There's nothing that is smaller in objective value than that last one. So in this case, there's no way of going back to the same basis. Why? Because the objective value is decreasing by a positive amount each time. So the basis matrices that describe these solutions are always different. If they were the same, of course, you would get the same objective value. Okay? So they are always different. So for that reason, no cycling can occur here. Due to having distinct bases in each iteration. No iteration, no basis matrix is visited twice. Okay? Now, with degeneracy, that's really not the case all the time. In that case, you begin with, say, z0 again. You may perhaps decrease for a while, I don't know, up to maybe, say, iteration. Let's make it j here, okay? And then, at this point, you may run into a degenerate basic feasible solution, in which case the objective value will not change for some time, possibly. And then you may get to an iteration, say, L here. And the sequence of bases you might have here, say, bj plus 1, so on and so forth, may be such that this one might be the same as bj. The last one, b sub l, might be the last one as bj. In this case, of course, if you don't change anything else, you keep doing the same thing over and over, unless you take some precautionary measures for avoiding that. Of course, you don't have to encounter this situation all the time. Sometimes you may stay in a particular basic feasible solution or in a particular extreme point through a sequence of changes of bases, and then finally get out of it, and then still arrive at an optimal solution. So it doesn't mean that this will occur all the time. Nevertheless, this is a possibility, and so if you don't want to go through an infinite cycle of iterations without doing nothing, then of course you want to take some precautionary measures for that. Let me give you an example problem where this actually does happen. So let's look at the example maximize 10x1 minus 57x2 minus 9x3 minus 24x7, no, x4, sorry, subject to 0.5x1 minus 5.5x2 minus 2.5x3 plus 9x4 plus the slack x5. The right-hand side is 0. Why is it 0? Because I want to make it degenerate, that's why. The second constraint, 0.5x1 minus 1.5x2 minus 0.5x3 plus x4 plus x6 equals 0 again. And then we have a third constraint, which has x1 plus x7, again slack, equals 1. So the last constraint is actually x1 less than or equal to 1, but we have the slack here. And then you have the non-negativity. Okay, so you begin with the slacks. That's my initial solution, the initial basic feasible solution. Okay, let's go with the rule of choosing the most negative reduced cost to identify the entering variable. And of course, for the minimum ratio, if there are ties for the minimum ratio, let's choose the one with the smallest index, okay, as the exiting variable. So let's just make a note of that for the entering variable, most negative. And if you have ties for the most negative, choose the one with the smallest index. For the exiting variable, smallest index among ties, if there are any. Okay? So in this case, there's only one choice for the entering variable, x1, and 0, 0. So going with the smallest index rule for the exiting variable, we pivot on that one. Okay? And then we arrive at the next tableau. I'm too lazy to fill in all the information. You can work it out on your own. because this is going to take 6 iterations to get to the cycle. You know, lots of iterations, but nevertheless, we have a beginning here. X1, X6, X7. When you pivot, you get 1, 0, 0, 0, 0, 1, 0, 0, minus 53, minus 11, 4, 11, minus 41, minus 5, 2 and 5, this one is 204, 18, minus 18, no, minus 8, minus 18, 20, 2 minus 1 minus 2, 0, 0, 1, 0, and 0, 0, 0, 1. And the right side, 0, 0, 0, 1. Nothing has changed on the right side. We're just in the same solution still. And then you choose the most negative. So you choose that one. And then you look at the ties. Well, you look at the ratios, sorry. In this case, there's only one ratio that qualifies because this is a negative one. Okay? So you pivot on that one. And then you get the new solution. Let me draw my tableaus because I want to make them fit. I hope it'll work out. 1, 2, 3, 4, 5, 6, 7, 5, 6, 7. So I guess I'm not going to make them fit. Too little space here. I'm going to write down the last tableau somewhere else once we fill this in. So in this case, this tableau has the following: x1, x2, x7, that's a 6.75 minus 0.75 minus 0.25, 0.75, 13.25, 2.75, 0.25, 13.25, 0, 0, 0, 1. And the right side, 0, 0, 1. Okay. There's only one negative here for the reduced cost, so you choose that one. And you look at the ratios. And the smallest ratio, there are ties, you choose x1 because of the smallest index rule. The next solution, you've got z, x3, x2, x7. Okay, again, we go with the most negative. That one is the qualifying one, and you pivot on that element. So this is the most negative one, and this one exits. Sorry, not that one. Sorry, I'm looking at the wrong column. This one exits, right? Okay. So we have Z. Which column is that? X6, X. Is this X3? This is supposed to be X5, I guess. Wait. No, okay. X3, X4, X7. Okay, X3, yeah, it's X3. X6 and X7. I have a problem here, just a second. There's something wrong here. Let me just check. This is the fourth tableau. Okay. This is the fourth tableau. Well, this tableau is incorrect. This is going to be the next tableau, so let's just swap these, okay? Because I made a mistake in copying down too much information here. So from here, you switch to this one, okay? And in that case, so that's why I've got some confusion here. I've got X3, X4, X7. We're moving to that one. X3, X4. No, that's a 4. X7. Yes, okay. 1, 0, 0, 0. 20 minus 2 minus 0.5. 1. 9, 4. 0.5. 0, 0, 1, 0, 0, 0, 0, 1, 0, minus 10.5, 0.5, 0.25, 0, 70.5, minus 4.5, minus 1.25, 0, 0, 0, 0, 1, and 0, 0, 0, 1. And here, of course, we choose this one as the entering variable. And then the exiting variable is 0 divided by that due to the smallest index rule. So from here, we move to that one. X3 is replaced by X5. 1, 2, 3, 4, 5, yes. So this has X5, X4, and X7. Let me just make sure that I have the correct numbers here. Yeah, looks correct. Okay, you pivot on that, and then we obtain a new solution, which is going to be the following. Do you have this? I'm going to pull it down. So the last one will be the following. X6 enters in place of X5. So we have X6 here. No. In place of what? Why do I have that? Just a second. Oh, okay. X4 is replaced by X6. X5 stays, yeah. X6 takes over X4 and X7. Yeah, this is what we have. This solution is the same as the initial solution. If I did not make a mistake in copying it down. Okay, it took a long time to write them down. Nevertheless, this is a good example which illustrates that cycling may occur. However, in practice, actually, cycling rarely occurs. Okay, so people usually ignore that. Nevertheless, we need to take care of that. And to take care of that, there are a number of ways of attacking that problem. The first suggestion that was made in the literature was to use the perturbation technique. And I'm not going to go through the details of that, but in the perturbation technique, what you do is, let me have your attention here. You have a system of equations, right? And you have the current right-hand sides with some zeros, possibly for basic variables. So what you do is, you add a little epsilon perturbation to some of the, or to the zeros, okay? Or to actually all right-hand sides. So that epsilon, if you add a single epsilon to all right-hand sides, it usually works, but sometimes it may fail. So you choose to add different epsilons, say epsilon 1, epsilon 2, up to epsilon m, to the m constraints you have to the right sides of each. In that case, epsilon is a tiny little number. which you need to specify if you really work it out numerically. But it turns out that you don't really need to specify the numerical value for that, as long as you take precautionary measures that the epsilons are ordered in the following way. For example, the first one is a real small number, but the second one is much smaller than the first one, and the third one is much smaller than the second one, so on and so forth, okay, up to the last one. These means much smaller, okay? And in the typical situation, people may use epsilon here, epsilon squared here, epsilon to the third power, so on and so forth, because epsilon is a small number. Of course, these inequalities will be satisfied, okay? So with the perturbed right-hand sides, what happens is, instead of staying in a degenerate extreme point, because of the perturbation, that extreme point is actually decomposed into a number of different extreme points, which are very close to each other, because epsilons are very small, okay? So different basis matrices define those different extreme points. And for that reason, cycling does not occur. The objective value improves by a positive amount in each iteration when you go through these. Now, it's certainly, that's the main idea. It's the details certainly can be worked out. Actually, some people did that. I think it was Wolf who first worked it out back in 1953 or something. I was born at that time, so I don't know the guy, but it was a long time ago. And some other people have also worked it out. So it works. And it turns out that you can actually prove that it works without having to specify the actual number epsilons or the epsilon i's, okay? They are just sort of conceptual. And that epsilon perturbation technique actually provides the motivation for the so-called lexicographic resolution of the degeneracy. So that's the first method. The second method is the lexicographic way of resolving the degeneracy. I'm going to tell you how this is actually worked out, but I'm going to omit the proof, okay? We don't really need it. It's just a numerical stuff which you don't need, unless later on, if you do a PhD or something and you start running into difficulties with your solver, if the degeneracy seems to be a problem, then of course you can go into the details to use these things. In the lexicographic method, well, actually, you can think of the lexicographic method as an implementation of the more conceptual method, the perturbation method, okay? It's the actual implementation. And we're going to go into details of that. And this was, I think, proposed in 1955. The first one was either 52 or 53. And the last one is the so-called Bland's rule, which is a very nice and, simple rule. I'm going to tell you what it is, and as long as, but this was proposed, this is an elegant rule. I think it was proposed, well, maybe 6 or 7 years after these things, okay? I don't remember the exact date now. Nevertheless, it came afterwards, and it's a good rule. So let's work on the lexicographic rule. So, in the lexicographic resolution of degeneracy, what you do is we assume, well, we use the columns of the inverse matrix. That's what we do to break ties. So let's assume you have the simplex Tableau, and let's assume the first m columns here are the initial basic variables. And so we assume we begin with the identity matrix at the beginning corresponding to the first m variables. I'm just assuming that they are the first m variables. So I'm separating that out. And this is the Tableau for some basis p. Okay? So we have R1, R2, Rm for the first m variables. And then you have a column here, another column, so on and so forth. This column has the vector y sub 1. This column has the vector y sub 2 and y sub m for the last one. And then you've got the remaining variables in the rest of the Tableau, up to the, say, the last one, x n. And among these variables, you identify, say, some variable xk as your entering variable, because for a minimization, Rk happens to be a positive reduced cost. Okay, so you enter that. You decide to enter this particular variable, and you've got your yk here. Okay, and on the right side column, you've got the current value of the objective function, and you've got the b vector here, specifying the current values of the basic variables. Now, I think we're just about out of time. So let me stop here. Let's take a 10-minute break, and then we'll continue with what we're doing right now.